So we listened to Pierre Ramond on models for neutrinos and particle physics.
Yes. Well, thank you very much to Daniel and Michel for their very kind invitation. And of course, I could not resist talking about neutrinos, since I spent a lot of my life with them, even before I knew. So several years ago, I was talking to a friend of mine who is an artist and trying to explain to him what neutrinos were, and he came out with three different things. One is mon premier neutrino, my first neutrino. This is a flirting neutrino. It's French, you know. And this is a neutrino caught up in an Argentinian tango. I will talk about four different things, and one will be starting with an editorial statement. The only one, I will have to talk about the early history. Then I will talk about what I was supposed to talk about, which are neutrino masses in particle physics. And then I will talk about, and this will be a butt to some of the work we've been doing on what neutrinos tell us about Yukawa unification, which is the fundamental theoretical puzzle left with the standard model. Okay? All right. Now, the neutrino was kind of born in a Greek way. It was born by revealed, I would say, wasn't born. It was revealed by pure thought in order to save a fundamental principle. And as a result of that, I think since it was not decided by direct measurement, and it was treated by suspicion by most physicists, because it didn't feel like it really came from experiment. It came from some guy, brilliant as he may have been, as he was. Yet, okay, if you go backwards in the history of neutrinos, if you study neutrinos, they're extremely important to the fabric of the standard model. First of all, they are left-handed in an ambidextrous world, and they lead to, parity violation is one of their traces. Secondly, since it was believed to be massless for a long time, a bunch of theorists, and I think most Volkov and Akulov devised a theory which is basically in which the neutrino was a Nambu-Goldstone boson. And it was a Nambu-Goldstone boson of supersymmetry. And their work came a few years after supersymmetry. It was a nonlinear realization of the idea. Then Pierre Fayet, who was local, was basically very interested and tried to understand theories where you could have a massless fermion naturally, and this drew him towards more normal ways of using supersymmetry. Okay, but the thing that was very interesting about it is that it was absurdly light, which questioned for a theorist, is that a sign of a new scale? And then, of course, we now know that large neutrino mixing, there's a connection with CP violation, leptogenesis, matter antisymmetry, but the question, are they key to Yukawa unification? And I would say that they are. Actually, the study of neutrino is very important because they carry a lot of information. In other words, they are very weird. They are very weird in a sense, and they're very useful because people talk a lot. If you want to get money in the United States right now, you talk about multi-messenger astronomy. These guys were multi-messenger before they were messengers. Starting from the sun, then we talked about 1987, and now we have Francis here who basically will talk about such things. And then the other thing is that neutrino masses and mixing, ever since 1998, are the only physics beyond the standard model we know of. The physics that beyond the standard model most people have been working on is basically wishful physics. It may be right, but it's not something. And what happens today is that a small portion of physicists only works on neutrinos, but not all people ignore the neutrinos. So first of all, the Nobels. There is Fermi, there is Pauli, there's Lederman, there's Schwartz, there's Steinberger, and then you need a second. Okay? Then there are Fred Reines, Ray Davis, Koshiba Sensei or Koshiba-sama, okay, Kajita-sama and art here. And then there are a lot of people who had the misfortune of dying too soon or contributing too soon, what I call the Hall of Fame. And these people contributed greatly to neutrinos, starting with Majorana in Pontecorvo, Maurice Goldhaber, Sakata, as I would argue, John Bacall, and Lincoln Wolfenstein. All of these people left their mark on the field, and even though they were not chosen for various reasons, some died too early, many of them died too early. Anyway, okay, now let's talk about early history. Now, there's the letter, and there's not much to be said about the letter. We've seen it many times, blah, 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 radioactive, etc. And of course, the important thing is that they do not travel with the velocity of light, so they have a mass, and that's because they were thought of nuclear particles, etc., etc. And Pauli writes this, but I would like to point out that he calls this a desperate measure, and the desperate measure had to do with inventing a new particle. Now, a new particle in those days meant that you were not clever enough to figure out what was going on with the existing data, and therefore it was desperate to invent a new particle. Nowadays, whenever there's a 1 sigma effect, there are 2 towers of elementary particles that come out automatically from about, I don't know, a large number of papers, but that's sociology. Okay? And I would like to point out that Pauli, the year after, in June 1931, there was an APS meeting in Pasadena where people who attended it, and I could not find this thing explicitly, but he did give a talk there, and his little neutron was still bound in a nucleus, and this is the way he thought about it. Of course, there were turmoil in his personal life. Not only did he divorce the actress Kate Deppner, but she married a chemist. That must have been very, very upsetting to him. And within a year, he was in analysis with Carl Jung. 2 years later, of course, Chadwick discovers the neutron. And then in 1933 and 34, Pauli talks about the neutron, Pauli's neutron as a free particle, the neutrino. And I was very happy that he was Italian, because if he had been German, it would have been a much longer name. Okay. Or French, for that matter. So I would like to start with a, Okay, well, this is 1936. Reviews of Modern Physics, Hans Bethe and Mr. Bacher, who basically, there is considerable evidence. I'll read it from here, but I will point randomly somewhere. There is thus considerable evidence for the neutrino hypothesis. Unfortunately, all this evidence is indirect, and more unfortunately, there seems to be at present no way of getting any direct evidence. At least it seems practically impossible to detect neutrinos in the free state. That is, after having been emitted by the radioactive atom. There's only one process that neutrino can certainly cause, that is inverse beta decay, beta process, okay, considering the capture of a neutrino by a nucleus together with the emission of an electron or positron. This process is, however, so extremely rare that a neutrino has to go in the average through 10 to the 16 kilometers of solid matter, etc. Okay? So this was the way. Now, I tried to look at least in the American Physical Society and Reviews of Modern Physics, when the neutrino, which was called N or N prime, small n or small n prime by the local practitioner, actually became new, Greek. The earlier I can see, there's an experimentalist called Ernest M. Lyman in 1938. He just calls it new, and I don't know whether that's the earliest time it is called new, but it is called new there. Okay? And then in 1948, there's still, to tell you the difficulty of acceptance, Crane talks about not everyone would be willing to say that he believes in the existence of the neutrino. Again, the belief word, you know. I mean, okay? But it is safe to say there's hardly one of us who is not served by the neutrino hypothesis as an aid of thinking about the beta decay process. I think that's a very fair assessment for the time. Okay? Now, so between 1953 and 1956, Cowan and Reines, called Project Poltergeist, detect first in 1953, they propose how to detect one of the free neutrinos, which is this inverse beta decay using an absorber, a neutron absorber, etc., etc. It's well known. And then he talks in 1954 about the status of an experiment to detect the free neutrino. And finally, in 1956, and that meant there was a fair amount of controversy as to whether or not he had discovered it. Okay, but in 1956 there's a confirmation, and Pauli writes, "Thanks for the message," which I think in 1954. Thanks for the message. Everything comes to him who knows how to wait. That may be a signal. Could be used for supersymmetry or something like that. Okay, now, all right. So. The next thing that is very important is a Chalk River preprint by Bruno Pontecorvo. This is somehow, well, anyway, it doesn't matter. So there it is. And Fermi, as it was recounted to me, said it's nice but not practical, which is actually very much in spirit with Fermi. Okay? But in 1957, Davis designs a pilot experiment at the Savannah River. Beforehand, as I pointed out before, is that Maurice Goldhaber was very instrumental in allowing a pilot experiment. And without it, it would not have happened. So that was very good. Now, Pontecorvo, I want to talk a little bit about this. So Gelman and Pais were the first to point out, so when that the interesting consequence which follows from the phi k and k bar, etc., are not identical particle. This is the well-known work, okay? And that, of course, since Mr. Davis, so there are two schools of thoughts. One of them is that maybe somebody said that Mr. Davis had seen a by the way, I should tell you, I'm in a southern university in the United States, and the neutrino is the only particle found south of the Mason-Dixon line, after all. Okay, so I have a special affinity because it was at the Savannah River thing. Now, the question is that he's very impressed by this, and as Shmuel talked about, basically that was a big motivator for him. And it turns out that this is part of what he talks about. And he talks about neutrino anti-neutrino transitions, which I did not see the word oscillation in it. Okay, but basically this is particle antiparticle thing. Okay, now Maki, and the reason I had Sakata there. Sakata, by the way, was a communist, and he carried his communist creed into his physics. Because he felt that all particles should mix. And there shouldn't be any, which is true. And so the question about mixing came naturally, and I remind you, Kobayashi and Maskawa come from Nagoya, which is where, they still have Sakata's office in there, untouched and everything. So this is part of the culture, and these people were completely right. Particles do mix. But that was somewhat of a novel concept. And they also talk about transitions, but it's flavor transitions and not particle antiparticle. This was 1962. And they're very, as Cecilia had mentioned before, they're very much motivated also by the Gelman-Levy paper, in which a footnote appears, and the Cabibbo angle is called epsilon. And Cabibbo refers to it in his paper, and this is how it goes. All right. Now, let's talk about what I'm supposed to be earning my money today. I got a free dinner out of this. And this is the thing about neutrino masses. Okay? So, all right. Now, Fermi talks about the first attempt, which is very, very famous. Okay? Talks about in two languages, in Technicolor. He has first the Italian language because he published his work in an unknown Italian thing called the Journal of Scientific Research, and it is said that he had been rejected by Nature, and then he publishes in a more serious journal. And so if you want to learn how to translate from Italian to German, this is perfect. And the other thing that is very interesting, this is an example of what I call extreme kinematics, which is a lot of my LHC theory colleagues do. We're looking at the edge of phase space and trying looking at the frequency of events in there, trying to actually determine actually the morphology of various events. But this was the first thing. And they are absurdly light. So this is very, very conventional. This is called the BEH boson. At least in some parts of the country, in Belgium, for example. And so there it is. This is the standard assignment. And now we can catalog this as we did a long time ago. Many people contributed. Is that since the neutrino appears in the left-handed doublet, we can take bilinears of the two left-handed doublets, and then we can form them in the antisymmetric in flavor as an isosinglet, in which case we'll have to couple them to some BEH-like object, which has charge -1. If it is symmetric, then it is an isotriplet, and then it has the same number of that, but it is what is it's called type 2 seesaw. I hate that word, but anyway. And what it is, this is something experimental. It's like a great deal because you have a doubly charged particle coming up. And of course, for an experimentalist, I think this is the easiest thing to do, a doubly charged particle, except it doesn't seem to be there. Now, and then there is this one, isosinglet, etc. And then you can do the same thing in fermions. You can do LH bar, and then you have so-called the real thing, which is the real seesaw, okay? And then you can do it in a different way with isotriplet things, leptons, which are couples to, in that particular combination. This is called type 3 seesaw. And that also has charged particles in it, okay? So this is a way of cataloging these things. And then the physics has a great deal to do by what happens in the potential. So the physics of this is determined into the potential in different ways, et cetera, et cetera. For example, there are all kinds of terms, so you usually have, if you have a cubic coupling, that means you have a dimensionful scale, and then you can do all kinds of, you can break lepton number there. It turns out the fourth order coupling does not break, et cetera, okay? As delta lepton number, total lepton number 0, etc. So you can, and people have been working on this for many, many years. This is what theorists do, usually, okay? After all, they have to justify themselves, okay? And then there are also models of which I think these are some of the names. You can also double the Higgs and couple it this way, and then etc. Then you have a flavor antisymmetric coupling, and then this is naturally suppressed at 3 level, and you get the mass at another level. At the end of the day, this has to do with trying to find out why the heck neutrinos are so light. Well, in this case, is what I call leptonic Higgs or leptonic BEH. What happens, the reason it's so light, because there's a scale that's put in by hand, which is the cubic scale, and that's all there is to it. Now, it could be coming up from some theory, of course, but at the moment it's what it is. Now we get to the mixing, the seesaw model, and as far as I can tell, I was just told yesterday, I did not know this, there was a paper by Minkowski, Gelman, and Fritsch, where they talk about both Majorana and Dirac masses and mixing in general terms without applying really, as far as I can tell. And then Minkowski talks about a bit later, and then we talk about it. And I have to tell you that when we did it in very early on in 1978, but Gelman thought it was such a crazy, stupid little 2x2 matrix that he didn't think it should be published yet, and we had to it was kind of complicated, but then a lot of people later on did it. And it turns out that coincidentally, on opposite ends of the planet, Yanagida-san and ourselves, we first put forth that, and then Shelley later on. Now, they are the type 2 and type 3, there are lots of names associated with this. And there are just a few of them here, okay? And then it keeps going. And so none of these things have really, well, they are there because it has been studied for a long time, okay? So let me now continue a little bit. Okay, so let me talk about the real seesaw. The real seesaw has to do with, so Dirac and Majorana unite, so this is a hell of a combination. I mean, it's very powerful. And what happens, the important thing is that it is a bridge. The suppression has to do, as you well know, with the ratio between electroweak physics and unknown physics, which we used to call it delta I weak. Weak is for weak. Half, which is electroweak, and 0 for unknown. That's the stuff. And the amount of suppression, and therefore the amount that you see naively, I mean, in the experiments, okay, at the milli-electron volt level, etc., tells you about this ratio of masses. Now, the important thing, from my point of view, is that what we were doing at the time, we were doing grand unified theories. And grand unified theories carried with them, I mean, there was actually the first grand unified theories. I didn't put Patti Salam, and that's an omission, but they are the first one talking about the fourth color, so to speak. And then there was SO10, and then there was SU5, then we had E6, etc. But SO10 is Georgi and Fritsch and Minkowski independently, and SU5 seems to have taken the fancy of everybody because it was simpler. But nevertheless, it's like that. But the fact that was very important, as Georgi Quinn-Weinberg showed, is that it implied a totally different scale. One of the legacies of the Standard Model is that everything is perturbative at the Z mass, even below. And therefore, you can use your techniques to go up to an incredible scale. And that was a kind of a revolution in thinking, because that meant that particle physicists became cosmologists, et cetera, et cetera. I mean, things that they didn't know anything about before. So let's talk about a little bit about the structure of this. Okay. So the first thing is that we have an important thing is that the MNS, we used to call MNSP, now now it's called PMNS, it doesn't matter. But the fact is that the observable angles have to do with the overlap between a unitary matrix that diagonalizes the charge -1 leptons and the seesaw. I mean, I'm not talking about the other things. Okay, I'm just talking about this. Okay, and this U-1, when you look at it, is diagonalized. It's from a charged lepton Yukawa. Okay. And this guy is diagonalized by using the seesaw. Now, this one, in principle, has electroweak physics coming from the Yukawas, and this one has physics we know nothing about. But the measurable angles are a bridge between the two. Okay? Whereas, for example, in a CKM matrix, you have the same thing, but it's a bridge between the charge 2/3 and the charge -1/3, which, after all, is the same kind of physics. This is quite different. And that means we have to understand this. So in particular, it means several things. So symbolically, when you have an experimental angle, which appears in there, you should, in principle, think of it as coming from its, I mean, this is a symbolic equation, right? That it comes from the seesaw side and from the electroweak side, and we don't know which is which. In fact, okay? All right. And the question is that on the electroweak side, the largest angle we used to look at is the Cabibbo angle, which is 13 degrees. Okay? And therefore, okay, that's it. The seesaw side, we don't know. Okay? But of course, the data is telling us, I think, a great deal of it. Okay? That's the theorist talking. Okay? No chi-squared, nothing at all. Just we have a mental chi-squared in our head. Okay? Now, whether or not it has anything to do with the price of cheese is another matter, but we have definite ideas about this, which are refreshed every so often. Okay, now let's talk about masses. Concha talked about the two particular hierarchy. I will only consider the normal one. And this is the data, right? I mean, the measurable things from oscillations, I don't know. The important thing is this. And now, one thing I do not know is I mean, this is at the level of tenth of MeV of electron volt, but we really need this at a much better level to know. But right now, it's just not very good. But nevertheless, it's the only thing we really have on this. Okay. Now, so let me tell you something about. Now I will go into my own research. So the reactor angle is about, I think, is less than Kabibo. Good stuff. Now, I don't know. You may argue about what that is. I like degrees. I mean, when I was in school, we never talked about the value of sine of an angle. In fact, we did not know what the sine of an angle was, but we knew what a degree was. So anyway, and the other thing is that we have experimentally we have two large angles, and I have to believe that this is due to this unknown physics that we know basically nothing about. Okay, all right, and of course we now know that there is one Dirac-like phase, and there are two Majorana phases thanks to Schechter and Vallée. Okay, all right, and now there are several. Now, as a theorist, you have a possibility to decide what you're going to do. Either the solar and atmospheric angle come, that is an extreme point of view, and the reactor angle, where does it come from? Now, this stuff here we used to call it the small thing. We call it Kabibo haze because there's this beautiful, supposedly this beautiful matrix coming from the seesaw, and then it was like, you know, like fog in Pasadena. I mean, smog in Pasadena, where basically you have a haze coming from this. But the question is in fact, is it a working hypothesis that this theta 1,3 comes purely from the Yukawa side? Okay, and this is what we've been looking. So now let me talk about this, the last part. In the last 20 minutes, I'll be talking about that. Now, so now Dirac's path, which we all follow, whether we know it or not, it seeks simplicity and beauty, and we now know, I mean, we know that we have that feeling in gauge couplings. I mean, a lot of people seem to have forgotten about this, but they are there. The standard model is arranging itself into things that look a hell of a lot like groups, okay? But then the question, we don't really know. We have complication in Yukawa couplings, and what a theorist's task is to match the simplicity in gauge couplings with simplicity in Yukawa couplings, because we believe that a great deal of the Yukawa couplings are, especially through the seesaw, are determined by this beautiful physics up there. Okay. So, but there's tension right away. This is why neutrinos are so incredibly interesting, because from the point of view, you know, quarks and neutrinos are the same. This is what, and leptons, charged leptons are the same because of asymptotic freedom. This is what Paty and Salam thought about. Okay? The gauge coupling seem to unify. I mean, and you can argue whether or not they unify exactly or not exactly, but they're going in the same direction. That is true. The Weinberg angle could have been completely different, and they could have gone one that way, one that way, but no. Okay? But then we have disparate Yukawa couplings. The small quark mixing angles are less than Kabibo, and the question about the big surprise from the theorist's point of view is that they have two large neutrino mixing angles. Now, we used to think, I mean, back in the very early 90s, I used to think there was one large mixing angles, but no, there are two. And the conventional wisdom, as you heard from the comment about Guido's Altarelli stuff, that it was impalatable. It's not impalatable, it's just that it's weird. But, you know, sometimes it's very good to eat exotic food. Now, so if you have large angle, naively, what you think about is a crystal. In crystallography, you have large angles, and you have usually point groups and stuff like that. You have a way of classifying this. So I think it's not unnatural to be thinking about this kind of structure. This was thought of a long time ago by Pagvasa and Sugawara and then Ma, and then since then about 1,000 authors, which I cannot write because it looks like an experimental collaboration. And there are more being added as we speak. And the question is that there are three chiral families, as we know, and so you look for symmetries which have three-dimensional representations. discrete symmetries because it's like a point group, and this was cataloged by mathematicians. And then you can look at SU3 or SU2 subgroups. SU2, of course, has the three-dimensional representation. And then there are several things, and I give you names which mean nothing at the moment, but anyway, this is how it goes. Okay, so I'm almost there. And I want to give you a very quick grain unification primer. Concha was very proud having put all these latex graphs in one place. Okay, and but I'm equally proud of this. So maybe let me allow you to suffer through it. So these are the Yukawa couplings with a right-handed neutrino. So these are the Yukawa couplings for up quarks, down quarks, electrons, and then the Dirac. Yes, ma'am. It's okay. All right, that's perfectly. Okay, now, and then there is this Majorana mass stuff. Okay, this is the way I look at it, and most people look at it, I think. Okay, so first of all, the data. Well, the up and down are linked by the CKM matrix. Okay, then you go on. Then if you put in the right-handed neutrinos, you have Dirac-like masses on this. Okay, and then when you have this, that is what SU5 does. SU5 links the charge -1/3 to the charge -1. Okay? And this leads to this beautiful texture of Georgi and Yaskog. Okay? All right. Then we have a U to D, and that's actually, oops, oh no, yes. SO10, the next group, actually gives you a connection between these two. Okay? In fact, with the simplest Higgs, these are the same Yukawas. Okay? All right. And then comes the seesaw, which actually mixes up this guy through an observable neutrino mass. Yes? And then at the end of the day, we have the PMNS matrix, which links those two. So in principle, theorists should be able to get something that is consistent. This is the consistent view given by grain unification, and using simplest assumptions. By the way, one should not use complicated assumptions because you're talking about physics at a very high scale, okay? And therefore, there things are supposed to be simpler. But who knows? Okay, so seesaw simplicity. What I mean by seesaw simplicity, and now is that basically that delta I weak equals 0 stuff is simple. There's some simple stuff. It comes from some symmetry, etc., and we have to learn. Okay? So what we say is that the small angle is all from the Cabibbo Hayes, and the two large angles are from the seesaw. And the seesaw is this pretty matrix. The tri-bimaximal matrix is a pretty matrix with an ugly name that Lisa Everett coined many years ago. And this was introduced, by the way, by an experimentalist. Mr. Perkins introduced this, okay, and his collaborators. Okay, so this looks like some sort of interesting thing. Okay, and in the simplest SO10, as I said, these are all kinds of relations. I don't have to tell you more about that. So now let me tell you one thing. Since you assume that the seesaw is diagonalized by tri-bimaximal, that puts a relation between the matrix elements, the 1, 2 matrix element, up to an overall the prefactors of those have all these relations. And now this is when you use a group, my favorite one is this one, then there's an extra relation that comes, which is this 2-2 element, and the 2-3 elements are the same, but it has an experimental consequence, which is that the mass of the second neutrino is twice the mass of the first. And that fixes everything. That fixes, okay? All right? But this, and this is the last one, okay? Now the question is, how do you realize tri-bimaximal mixing? And I will quickly run through this. This is work we have done. And the thing is that we have here, so this is the 5-bar Yukawa matrix, looks something, and this is in a Wolfenstein language. What the heck is this? Okay. All right, and what happens is there's a totally asymmetric case. These are all the Wolfenstein parameters. You find that with this particular matrix, all the values at grain unified, MB equals M tau, M mu is 3ms, MD is 3me, which are the Georgi-Yaskog things of the 1970s, okay, are satisfied. And you find that the PMNS angles turn that now you can compute, okay, assuming try by maximal. This one comes about 2 point some degrees above PDG. This is 2.9. This is 6.6 above PDG. But, okay, but you need a phase. So you can use the phase to reduce the value of theta 1,3. If the phase, this is a TBM matrix, has the cosine of which is 0.2, that brings theta 1,3 to its PDF values, and all the other angles fall in place, and the Yaskog-Greenberg invariant absolute value is right on the money, much to our surprise, okay? And this gives us delta CP, but we don't know the sign. We cannot say because the only thing we fix is the cosine. And the sign, it's either delta over pi is either 1.32 or 0.67. This is certainly wrong by experiment, but this is certainly very much in contention. And I don't know exactly what most people think it is 3 pi over 2, but maybe it's a little bit less than that. I don't know. So this is rather interesting. And to our surprise, we were able to get this to work. Now, these are the experimental stuff. Then I want to make 2 points, and this is what's very important. So I have one prediction, which we talked about. But the first thing is that the sun never sets on neutrino detectors, which means that you save a lot of building material because you don't have to build any more temples to make sure that the sun rises again, because you know where it is at the Y. So there's progress, okay? And then I want to make a prediction, okay, which will be important in terms of the next speaker. Let's see. Okay. But I made the prediction. So, okay, first of all, oops, excuse me, and then I'm finished. So let me talk about neutrino chronology. This is a string-inspired prediction. First of all, the revelation is 1930. The detection, 1956, and the confirmation, which is 2 times 13 years later. Oscillations, 1998, which is 2 squared times 17 years later, okay? And therefore, as a good string theorist, which I used to be, okay, basically what you need to do is to say, well, what's going to happen the next time? So this is 2 to the 3 times 19, because you increase the prime, etc., okay? All right? And that's neutrino-less beta decay. And when you compute it, it's in 2052, in which case maybe somebody in this audience will still be around, but I'm afraid the rest of us will not be there. And so that's about it. And it means that longevity is required. Neutrino prospecting should be a family affair. I mean, you should train your children, if they are at all trainable, okay, to basically do the same stuff, okay? And I will finish with an anecdote I should have said about Pontecorvo. My colleague, and then I swear I'm finished. My colleague, Gena Mitzelmacher, was a student, my colleague, Gena Mitzelmacher in Florida, was a student of Pontecorvo. And in fact, then he became, he's an experimentalist, went to work at Delphi, then went to work at the SSC, then went to work at Fermilab, then went to work at Florida. And so Bruno Pontecorvo had several sisters, but also 2 brothers. One brother was a biologist called Guido, and the other one, Giulio, I don't know how you say it exactly, was a movie maker. And so when Bruno Pontecorvo went to CERN, he asked Gena to drive him to the chalet of his brother, his biologist brother. And so he did. And the biologist brother was a very distinguished man who had won the Darwin Medal of the Royal Society. Spent a lot of time in Glasgow. And so the 2 brothers embrace, okay? And so Guido, the older brother, asked him, how was it? Talking about the Soviet Union. And Bruno says, so. And the older brother said, I told you not to go. It's true.
Ali, I want to congratulate you for your first usage of a laser pointer. My question is, can you predict in how many years we will be seeing the right-handed neutrinos?
That's much harder. This is the next time. 2 to the 4th times 20 times 23.
23. 2 to the 4th times 23.
Yeah.
All right.
What kind of question is that?
I have a question in a similar vein. In one of your early slides, you talked about the first appearance of nu in the journals, right, written for Neutrino. Now, how did you learn that? Because if you just search all of the literature looking for the letter nu, you're going to get an awful lot of H nus that you have to remove before you get this hit. So how did you do that?
Well, I did it the hard way. I mean, the physical review, I only looked at the physical review, and I looked at a lot of papers that were written at the time. There were very few papers written on neutrinos. There were many more. So I read lots of stuff, and then I went and looked at people talking about neutrinos. Okay. Now it could be that someone else did. I mean, I checked the original papers. Somehow I missed the Majorana slide. I don't know. Anyway, somehow it disappeared, but Majorana was there. It could be that some Italian journal had it. I don't know. Majorana certainly never talked about nu. In a paper with Bete and company, it's called n prime, small n prime, etc., etc. So this is the earliest one I know of, but that may not be true. But in so doing, I read a great deal of stuff about the literature of the time, and I read, but I was just curious, but I'm sure I thought some famous person had done it, and then everybody followed. And it's true that after that time, somebody did. But I don't know. Yeah.
Last question, maybe.
So if we measure delta, and/or my granddaughter measures my neutrinoless double beta decay, and maybe even we get the phases, what do we learn about the seesaw mechanism and/or leptogenesis?
Good question. Well, first of all, this stuff here is very much a bottom-up approach. I think what one has to do now is to go look for theory in which this comes out. Now, the search for theory, I haven't spoken about this, because that's another talk, and it's really far out. And the question is that this is at the point where then you start having some understanding. So, for example, when you compactify from higher dimension to lower, you are coset manifolds, and you don't quite know very much about them. For example, in Calabi-Yau, you only know the topology of them mostly. The rest is very hard to compute. But the question is, do discrete symmetries come up? Well, it turns out that some of these groups, for example, the PSL27 is ubiquitous in mathematics, but that doesn't mean anything. So the task of a theorist, most string theories completely disregard the Yukawa part. I mean, for them, the standard model is basically the gauge coupling. And then, the hell with the rest. Well, I mean, okay. So it's not finished. It's not finished. But right now, I must say that if this is measured, if the phase is measured with some accuracy and it comes out like this, I think you have to pay a great deal of attention to this. But in order to interpret what these matrices actually mean in terms of fundamental theory, it's just a bridge now. The next question is not answered. Now, Sergei will talk about something quite different. But all we're doing here is just on the effective field theory stuff, more or less. We are just looking at the couplings, effective couplings, But effective couplings, just like for example, Weinberg's effective coupling, you don't know where it's coming from. You just know it's allowed, okay, and that's all. So there is a lot of theory now. That's why it's very hard, and unfortunately, And neutrinoless double beta decay. Well, if it is normal hierarchy, lots of luck.
A lower hanging fruit is CP violation.
Yeah.
What could that bring to your future explanation?
Well, you have to the CP violation. I mean, we think we know now in this particular way of doing things. And we know what delta CP is, 1.32 pi plus or minus, but you know, it's kind of close to, it's within the window, but it doesn't mean anything. Concha mentioned that actually, well, it's a minus pi over 2, but then there's a bit of shift. Who knows? I mean, frankly, we cannot say right now.
The precise value, the knowledge of the precise value will be of...
Yes, you're talking about the precision. Well, yes. I think the really interesting question from my point of view is that theta 1,3, okay, is a kind of a watershed measurement from the point of view of theory, because, for example, when you try to fit everything together, theta 1,3 is very annoying, okay, the value. And so, for example, things such as the ratio of electron to muon masses and theta 1,3 are related in those things. Okay. We have to work more on this. But how accurate must it be? I cannot answer that to you.
Okay, so I think we will discuss again this point with Sergei's talk. I think
Thank you.
we need to move on. Let us thank the speaker again.